Welcome to module 11 of object oriented analysis and design. In the last couple of modules, we have discussed about different elements of object models. We have seen that there are 4 major and 3 minor elements which will guide, which will be the principles on which object models should be built up. Based on those, now from this module onwards, we will actually get hands on with starting to define the details of objects, their relationships and classes and the relationship of classes, and slowly get into actual exercise of identifying objects and classes in an object oriented system. So, here in the current module, we start by discussing the nature of an object. The objective of this module is to understand the 3 aspects known as state, behavior and identity of an object. Outline is given here, and like in every module will be carried on the left of every slide. So, just to quickly recap what is an object. Now, we have talked about objects in terms of abstraction. Now, if we finally want to come down to design, then what we say will be an object. The first condition or the first concept that we will try to enforce is that object must exist. There must be some kind of an existence for the object. So, objects could be tangible, that is we can physically touch them. It may be somewhat intangible, for example, a process being followed in a manufacturing company could also be an object. You certainly cannot touch the process, but it exists. It could be visible, it may be less explicitly visible and so on, different various aspects, but fundamental to everything for an object is it must exist. The second is an object that exists must interact with others. That is, a system is not interesting if it has objects which just exist by themselves and do not do anything with others. So, if a car has objects like steering, like body, like engine, like wheels, like seats and so on, these objects must interact between themselves, and that is how we will get the existence of a bigger abstraction or a bigger object like a car. Third, and a very important factor is object must be distinguishable. That is, it is not like the dust in the air or the water vapor in the cloud, but it must be like people, like chairs, tables, items, processes, practices and so on. So, that one object must be distinguishable from another. So, these are the basic premise on which an object will be identified. Now, certainly it will be in order to also talk about if these are objects, then certainly there is a lot which is not an object, and what is not an object is certainly a more fuzzy, somewhat vaguely defined concept, and certainly something that does not satisfy one or more of the aspects that we just talked about will not be an object. For example, suppose a car has an engine. So, if we just look at it has an engine. So, naturally an engine is an object, it has a steering, that is an object, it has a body, that is an object and so on. Now, we can say that the engine of the car, I want to put this information in the design that the engine of the car is imported. Now, the fact that the engine of the car is imported is a property, and being imported is not an object. Kindly understand that this is different from import, which will be an object, but here we are saying that the fact that the engine is imported, that it is manufactured outside the country and purchased from there, is a property and is not an object. Similarly, say that we have a power steering. So, we say the steering is driven by power. This fact will have to be somewhere put into the model, put into the design, but it is again a property and not an object. The color of the body of the car is red. The fact that it is red is a property and that is not an object. So, there you could slowly think and expand on this, and you will be able to identify, you will be able to reason to yourself that what is an object and what is not an object. Now, if I say this is, we now understand what is an object, then we ask what does an object have. In object oriented analysis and design, from that perspective, an object is an entity which has three basic parts: a state, a behavior and an identity. The structure and behavior of similar objects will be defined in terms of their common class, about which we will talk more in the following modules. And just for your reference, the terms like instance of a class and object, we will be using them interchangeably, one in place of the other. So, now we will take a look into what are these state, behavior and identity of an object are. So, first talk about the state of an object. The state of an object is a combination of the values for its properties. Just note. So, it is dependent on the properties, and a state will be given by the combination of the values that the properties have. So, if I have a complex object, complex number object, it has these two properties, real part and imaginary part. Then a state will be, since it has two components or two properties, a state in this case will be a pair or a doublet, giving the real part and the imaginary part, and all different states, potentially infinite, all different such pairs will define different states of a complex object. That is a simple idea. That is, you consider what the properties are, consider what all different values they can take, all of these combinations give you a state. Let us look at a little bit of a different object. Let us look at a date object. So, here we have, I have just put a date object, simple date object, which has the date as in the number of the particular day in a month. So, it can be between 1 to this notation means that date is a property which takes a value between 1 up to 31. This is defining a range. It has a month which is 1 to 12, and just arbitrarily I have taken a 500 year span, 1700 AD to 2200 AD. So, a date object will have these three properties. So, we can look at different instances, different objects having these three properties, like 20th July 2016, 15th August 1947 and so on. These are all valid dates, and therefore, each one of them define a valid state. But we said the state is a combination of possible values that the properties can take. So, for a date object, these are also possible values, like 31st June 2016. We all know that is not possible. June cannot have more than 30 days. So, this state for the date object is an invalid state. Similarly, 29th February 2003 is an invalid state, because 2003 is not a leap year. Very interestingly, in the calendar that we follow, if you try to find the date 12th September 1752, it will actually be an invalid date, because it so happened that the calendar moved and 11 days from 3rd to 13th September in 1752 were simply wiped off out of the calendar. So, the reasons could be all different. In some case, a month does not have enough number of days, in some cases a leap year has to plug in some case it is a one time change in the date calendar that happened worldwide, all these lead to the fact that states may or may not be valid. That is, when we talk about all possible combinations, there is some underlying set of constraints that kick in to define what is a valid state and what is not a valid state. So, let us look into a little bit more of this. Here I have framed a collection of example objects for you, where first you consider the similarity. The similarity is all of these objects have two attributes, two properties, all four of them, and both of these have the same type. So, if I just consider the possible combinations of values that the properties can take, all of these objects is expected to have the same set of states. But now, let us think of it semantically with the meaning. My first object is the first quadrant in the Cartesian. So, naturally all possible coordinate values are acceptable, they are valid. So, all states are valid. Now, think of a fraction. A fraction naturally is represented in an irreducible form, which means that the denominator and the numerator must not have any common divisor. The GCD of these two should be 1. So, in terms of the properties, I can write 1824 as a pair, where 18 is the denominator, this is the numerator, is actually invalid, because they are reducible. Whereas, when I actually divide them by the common factor, it becomes a valid state, a valid fraction object. Proper fractions similarly would be those which are less than 1. So, 7/5 would be an invalid proper fraction. If I think about a chessboard which is 8/8, naturally each component, each property of the chessboard must be a number between 0 through 7. So, all other states like 9/8 will be invalid state. So, what it shows that it is not only the properties and their types, but the state is dependent on some kind of hidden constraints or some kind of encoding of objects exist in those hidden constraints, which actually define what the states an object can have. So, this in every case, whenever you design an object, you will have to implicitly at least understand what the states are and what the validity of the states are, and more constraints you actually have, which is incidentally often are hidden. So, they are not explicit in terms of the object design, not at least the way we have seen so far. Then you will have to make sure that you do not do a design which allows invalid states to become possible values in your system. If it happens, then you will certainly have different kinds of error coming from the system. Let us take a little bit of a extended example to understand some more depths into the state. Let us consider that we are at the outpatient department of a hospital, which is 2-storied. It has a ground floor and a first floor, or floor number 1 and floor number 2, and there is an elevator which plies between them. From ground floor it goes up to first floor, from first floor it comes down to ground floor, and there is an elevator object. So, this is the elevator object. So, it talks about different properties like the make of the elevator, the model, the maximum number of persons it can carry, the maximum load it can carry. Certainly, it defines a basic, these properties define a basic elevator. But the question is, do these properties actually define an elevator? When we say it is an elevator, we expect not only information about which company made that or how many persons it can carry and so on, but we certainly want the basic elevation and derivation functionality to be available, that is, it must move up and down. Okay. So, just to explore further, let us see what will be the impact on the state if we add these operations, add this functionality to the elevator. So, just look at what I have done, this remains same, this is exactly what is there, but I have added a number of operations here, added a number of behavior to this, which say that I have a method up, which if pressed will make the elevator go up from floor 1 to floor 2, similarly a method down to go down, a floor method could be there to check which floor the elevator currently is in. It can check whether the elevator is moving or it is stand still. I could stop the elevator, open the door, close the door and so on. So, these are all, there could be several other operations, but I am just focusing on some of the typical operations without which an elevator does not become an elevator. Now, look into the state information. This is your state information, which says make, model, maximum persons and load. And this is the functionality that we actually want in the object. So, we can easily see that the state is inadequately represented to carry the behavior. For example, if I have to go up, I need to be on the ground floor or floor number 1, otherwise certainly I cannot go up. So, to go up I need to know which floor I am in. To go up, certainly I would not like to go up in an elevator where door is open. So, I would need that the door has been closed before the elevator goes up or it goes down and so on. So, for these operations to be meaningful, I will need an extension of the state in terms of a number of additional properties that this object should have. For example, it should have a property say floor, which could take 3 possible values 1, 2 and x. 1 when it is at the ground floor, floor 1, 2 when it is on the second floor, and x when it is moving, that is its floor is indeterminate. Similarly, it could be still, it could be going up, it could be going down. So, is moving is a property which will say that the door open will be a boolean if the door is open or is closed. So, these properties will help all these different operations to be actually realized. So, with this naturally the state of the elevator now gets extended. So, now if you look at these are the states or properties that we had, and these are the properties that we have added. Naturally, with this addition the possible states of the elevator becomes a lot more, but you can see something, the reason I am coloring them blue and red is you can see something about the elevator object. See the blue properties, once an elevator has been installed in the hospital, then certainly its make, model or the ability to carry the number of persons or the maximum load it can carry, these properties are not going to change. This will remain same as long as that elevator is in operation. Whereas, these properties, the red properties that we have just added, the floor is moving, door open, these properties will regularly continue to change, their values will continue to change as the elevator every time gets into operation. So, we can say that in terms of defining the state, there is a set of static properties which does not change or very rarely change for an instance, whereas there are dynamic values for certain properties which changes regularly. So, naturally when I talk about the state of an object, it is whenever such situation exists, it is more interesting to talk about this dynamic part of the state instead of talking about all possible values that can take part and define a huge state space of possibilities for the object. So, this is we will talk about these kind of diagrams later on when we talk about UML, but this is just a simple representation to show the different states an elevator could be in. For example, initially I could be here, that I am in. So, this representation is like this. Within every circle which denotes a state of the elevator object, I write 3 items. The first one designates the floor, the second designates the moving status of the elevator, and the third designates what is the status of the door. So, if I am initially here, then it is 1 still open, which means it is in the ground floor, floor 1, it is still, it is not moving and the door is open. So, at this stage what you can do, certainly at this, in this state you cannot go down, because it is already in the ground floor, but you can go up. If you go up, so this is the action that you can do on this state, and then the state changes to something like this, where the state becomes indeterminate, I am sorry, the floor becomes indeterminate because it is moving, your direction becomes up because you are going from the floor 1 to floor 2 and your door must have been closed. So, when this transition of state is happening, then this values of these properties must change in the appropriate way as shown. Similarly, when the elevator comes to a stop, because a stop operation has been performed, naturally the floor of the elevator must have become 2, because it was moving up, and it becomes still and the door is still open. Now, if people want to go out, then certainly they can do an open operation and the state changes to 2 still open. You can switch between these two by opening and closing the door, or you could from any of these states you could put down, keep the elevator moving again, but now in the downward direction and finally reach the floor 1 or the ground floor and become stationary. So, this is we will see, this is called a state diagram or state, subsequently we will see this will be called a state chart in UML. These are very powerful tool to represent how the state of an object could impact the behavior of the object in a very second manner, how the constraints will apply. Here you can say find that though we are having 7 properties in total, the 4 make, model, maximum persons and maximum load are ignored in considering the state, because they are kind of static properties, and the 3 that we have which are dynamic values, even there we do not take into consideration all of the possibilities, because all of the possibilities simply cannot happen. For example, I cannot have a state where I have x, I have still and I have open or even close. That is, if my floor is indeterminable, then my elevator cannot be in stationary mode, it must be moving. So, this will tell you that this kind of representation of states implicitly encodes the constraint that exists, that an elevator must be at a well defined floor if it is stationary. If it is moving, it must have an indeterminate floor. If it is moving, the door must be closed, and so on and so forth. So, that is the kind of state information that an object would carry. So, to summarize on the state, we will say the state of an object encompasses all of the usually static properties. We have seen usually static, the kind of properties we saw for the elevator of the object, plus the current or usually dynamic values, that is the floor is moving kind of properties, and that together will define the state of an object, and the state of an object may be valid or it may be invalid based on the constraints that are encoded by the state. And our endeavor would be to design and define systems and their operations in a manner, so that we always move from one valid state of an object to the next and so on, and we do not ever get into an invalid state. Getting into an invalid state is generating an exception in the system, because if an object is in an invalid state, that is, if an elevator is moving with its door open, then certainly the system would not know what could be the valid operations for that, what could be a consistent way of moving forward with that system. Now, Along with this, we should also note that the state actually satisfies the first condition that we talked about the object, that an object must exist, that is all objects within a system encapsulate some state, and all the state within the system is encapsulated by objects. This statement is very simple, couple of words, but this is a very deep statement, and please read it over and over again. Try to go through examples to see that all that is being said, that if a system comprises a number of objects, then every object will encapsulate some state in the system. And on the other hand, the total state of the system, if I think about the whole system as an object, the total state of the system will be encapsulated by one or more objects in different parts, and that is the basic notion of states in the system. So, now therefore, every object that I have in the system must have a state. Now, if it has a state, then it has to take up space. A state is memory, state is remembering, state is knowing in what condition I am. So, a state will always need some space, takes up some space, very important. That space could be in the physical world or it could be in the computer memory. The elevator in the OPD of the hospital physically exists. So, it has states, it is supplying people between the two floors, opening, closing doors, moving up and down. It has a physical existence, the states have resulted in a physical existence. So, it exists in the physical world. On the other hand, when I would like to design and implement a system for the whole hospital, taking that elevator as a part, this elevator object will become will get an existence in the memory, where in the computer memory I will have binary bit representation for all these different properties, and we will do something about the methods, so that it will occupy certain bits in the memory and it will have an existence. So, critical to take back from this is states imply that objects finally have to have space, finally have to have a physical existence, however abstraction we actually talk about in terms of their characterization, in terms of their design. So, if we just look at a very simple some simple kind of example, talk about our leave management system, then every employee is an object and will occupy separate space. Now, naturally physical employees of course will occupy space, but their object representations, as in here I have one employee, here I have another employee, John and Linda are two employees. Their objects will be represented in computer memory with all these values, and they will take up physical space for that. So, with this we come to the end of this first part of nature of objects, and here we have just discussed about the state. Next we will talk about the other two aspects of objects.